So I will be basically focusing on two parts. One is B physics results and the phase 2 detector upgrade. So it would be like half and half. Even though I have written it's a B physics at CMS, there are few analysis results I will show is not quite B decades, but we carry out in the B physics groups, and those are also very interesting. So now going to the next slide. So this is the CMS collaboration. I do not want to go over anything except saying like we have more than 50 countries with close to 250 institutes. And India is participating, one of the CMS participating country, and we have about 160 out of, you see like about 5,000 active people participating in CMS. And we get close to 150, 160, 170 people participating in CMS over 14 institutes, different institutes. And that's LHC, and I am sure you have seen earlier in the regular school time, and yeah, that is one of the collider underground, the 100-meter underground, where you take the protons and collide them. And I will come back next. Actually, the detectors around the collision. So this is the CMS detector around the collision point, and the center here. Can you see the cursor? Because that's very important. Can you see the cursor?
Yeah.
You can see the cursor. Okay,
yeah,
thank you.
yeah,
yeah. So so there is a collision around the central point, and then we have different detectors cylindrical around the collision points. And this is the cutout version of the CMS detector. And but if you go the radially outward, it has several sub-detectors with a different detector mechanism to identify or recognize the particles. So this is against the central point, collision point, with a different pixel or tracking detector, electromagnetic calorimeter that is shown here. And then you have a hadron calorimeter, and then solenoid. And you have iron yokes with in between detectors actually pushed in to identify different particles. And there are the different detector components with different descriptions, like what is the detector size, or if they are made up of silicon tracking, what trackers, what are the pixel size or strip size. As well as muon detectors are made up of different sub-detectors like drip tubes, resistive plate chambers, and CSEs. And these are some brief descriptions, and I will not go over all of them except while I come back to upgrade time, I may just mention few parts of this. For the students, I have put a few 2-3 slides for the people who are mostly students and working theory. The experimental students, they know quite a bit of detector mechanism. So I put a couple of slides about analysis methodology we follow in the different searches. Sometimes you look for the physics where you try to validate the standard model prediction, but there are certain cases you want to find something beyond standard model. And they are a little bit different things, and we have different, in fact, all the experiments follow not the same, not unique procedure. So I will just come back to it. Now coming to the detector, so this is the view of a real detector, so opened up view, and that is, you can see that it's in between there is a beam pipe, and they have kind of opened up. And when you pushed it back in, and then you get a cylindrical detectors with the different sub-detectors radial coming out, you can see. How does it work? For our detectors, it's very different than that you heard from morning, like Belle II and other experiments. Certainly, all of these detectors have a magnetic field to bend the particles, otherwise you will not know which particle is what. They will just straight come out from the center collision points. Apart from that, we have tracking detectors in the innermost, which job is basically to find out not only to look at the tracking parameters, but also find out the vortex. And the other one is basically we have so basically when the charge particle go through, you just it just leaves the sign there, and then you keep it in your data, and then just fit it, and they see actually how the track looks like and where it is coming from also. And that's why it is very important. You put the detector as close as possible to the beam pipe. At the same time, you have to be careful, because as you go closer and closer, you get more and more radiation exposure also. So you have to make a balance. And these detectors are super thin, and I will come back to it. And then there is a calorimeter, where we have electromagnetic and hadron calorimeters, where when the particle go through, they just create the showers, and you collect the shower information. That gives you basically the energy information. That gives you basically initial energy of the particles, and that's the whole idea of the calorimeter. And we have actually the final last one I was showing, the outermost was the with the iron yolks. There are muon chambers, and we have 3 different muon detectors, drip tubes and RPCs and cathode strip chambers. And I just showed their mechanism, how they work actually. They pick up the signals from when the charge particle go through. So we do not have a particle, unlike Belle and the Browder detector. So we do not have a particle identification system where it says this particle is kaons or ions. So when you have a tracks, we will not know. So with these detectors, we have collected about 114 inverse femtometer of data total, with from 2010 onwards till last many years. You can see that this is the integrated luminosity, or we call it the data size. So the 2016 has the higher data size, and there are quite a bit of analysis that is. So 2016, 17, 18 collective data, we call it like Run-2, and partly 2015 has very small data. So now this Run-2 data has a lot of physics results that is yet to come out, and so we'll just see few of them, but I think a lot of them will also come out soon. The total recorded luminosity, not only 13 TeV, including 7 and 8 TeV over 2010 to 18, was LHC delivered about 193, and we recorded it close to 95%. So we have very good detector performance, where we record a large amount of data that is provided to us by the LHC team. The bottom left shows the luminosity in the hertz per nanobarn. So 10 to the power, our design luminosity is 10 to the power 34 per centimeter square second, which is basically 10 hertz per nanobarn. And you can see around in 2018, we have gotten almost twice, a little more than twice actually, the design luminosity. But at the same time, when you have larger, more luminosity, then you allow this large number of particles. So this is basically mean number of proton-proton collisions. So we have a proton comes in bunches, and each bunch has about 10 to the power 15 protons. And this is the number of protons collide. On average, number of protons collide every time one bunch pass by. And so about average 35 to 40 in 2018, 35 to 40 protons collided in every time bonds crossed, and then after that they just come back again and then collide again. And you can see over the time from 2011 till 2018, as you increase the luminosity in on the left side, you see here, as you increase the luminosity, that also makes this number of particles interactions per bonds crossing gets increased, and that creates more challenges, because you have like, as you now if you go to higher luminosity and the number of proton-proton interaction goes to 100 or 150 or 200, that creates a lot of challenge for our detector to collect the data and to keep up with the data taking, so that we collect a lot of good, interesting physics events. And CMS has so far published more than 1100 papers. I mean, some of them are submitted, still not accepted, but more than 1100 papers are there. And I will be talking about a few B physics results, from the results from the B physics groups. And some of them are in the context of, I want to talk about those results in the context of motivating to go for the high luminosity LHC and the detector upgrade. In that point of view also, I want to discuss, there are several Dighe modes that are very interesting. So so let's talk about the B physics, what happens. So we have a very big, this is the total cross section for the proton-proton collision. And the B cross section is one of the largest. And then we have, for the heavier massive particles, the cross section gets lower and lower as expected. So the B production cross section goes, if you look at the tevatron to LHC, the production cross section goes close to order of magnitude higher, and about 100 microbar. But it's not the production that matters. Actually, it is matters which decay you are looking for the B decay modes. And in this plot, there are the other cross sections are mentioned, and some of these points you see the breaks are there because there were theoretical prediction for when the tevatron was running, but then the LHC runtime, the theoretical prediction was made, and then I think some of the cases it just merged nicely, but some cases there was you can see there is even though for same production cross section, there is a gap between them because they were estimated in the different times, and there may have been some theoretical improvement over the times. What do we do? So now we have B quarks and leading to the B mesons, and then and we produce a lot of these B mesons depending on the production cross sections. And how do we do analysis and normal in the LHC or in any, for that matter, any experiment? So if you want to look for some final state in the B decay or in even the Higgs going to 2 photons in anything, any of these physics final states, first thing is basically you have some online selection procedure. You cannot have all these huge amount of data to be collected by your, you cannot save them. So you have to have some online selection procedures, and that we just call some trigger selections. Then you look for the if you look for the B decaying to 2 muons, for example. So you try to find out in that trigger selected events where you have 2 muons. And if your analysis is more aiming towards looking for something like new physics and looking for beyond standard model new physics, then you blind that region because and then you just do try to estimate the background that will come in your signal region. And then after that, you unblind the signal region and find out how many events you got actually. That is the standard strategy most of the time we follow. But if there are some really standard model, you are validating standard model processes then normally, and you have enough statistics, like thousands of statistics, and you are really validating the standard model branching fraction or the production cross section and so on. Quite often people don't have to blind them. You can just do unblind analysis also to start with, and that's also. And then in the end, just perform the statistical analysis and interpret the results. So one of these, so I will talk about 4 or 5 of them, and one of them is basically BS2 MIMU, and I think it was covered very extensively. I will not go very details. So this is one of the best place to find the new physics is basically the rare decays, because most of the rare decays, they don't go through the tree tree-level diagrams. They go through the loop diagrams, and that's why they are there. And in that, for example, on this case, and if in the loop you have, instead of the standard model particles, if you have a BSM particles, then they will contribute to your amplitude, and so also your all the experimental observable, including the branching fraction, and they will just change. They will differ from the standard model prediction, and that's what you want to look for. Actually, that's one indirect way for looking beyond standard model physics. And this process is not only it is only processed through loop diagram. It is also suppressed because of the helicity, because as you go to BS to tau tau to mu mu and EE, go to lower and lower mass, and towards massless limit, you are just forcing one of these muons into the wrong helicity state. For example, mu plus, you are forcing it to be left-handed. As it goes to massless limit, it should be more towards right-handed as it's antiparticle. And then there is a not only BS, then there is a BD going to mu even further suppressed by the CKM elements, and this is the suppression in the amplitude, and the cross section will be suppressed by a square of the amplitudes. So all these, because this is such a rare decay, it will really impact. If you measure in your data, you have enough statistics and you measure it precisely, and it can lead to, and compare with your standard model prediction, that would really give some hints of the BSM physics. And this is one of the cleanest rare decay, both experimentally and theoretically, in a sense. Well, we'll see how much clean it is, but experimentally, it's just in the event you have to look for 2 muons, nothing else. And theoretically, it's 2 leptons. The B measure going to 2 leptons, so the uncertainty in the hadronic side probably gets suppressed. And so the theoretical prediction, you can see the level of uncertainty in the theory. BS to mu is about 0.14, and the BD to mu further, it's suppressed further lower, it's by 0.05, the central values. This because of the importance of this analysis over the to look for the beyond standard model physics, which is experimentally and theoretical such a clean process, people have been searching for last 35 years, and these are, each of the dotted points are basically one of the publications by starting. You can see Clio, Argus, EO1, to CMS, LHC, Atlas, and this is not the updated one, by the way. So in the right side you see till 2015, but we have now CMS Atlas and all these CMS Atlas and LHC combined result, as well as CMS results also in 2020, and that was not included. But that all these things brings this limit to further down and down. For the BD and BS, we have measured this branching fractions. And so what happens? So I want to talk a few of them in a little bit more detail, so that specifically in the interest of the students, is what you want to look for is 2 muons coming from the same point, because it is decaying from B. So it must come from the same point. And because B has some flight length, they should basically the vertex from primary vertex to B vertex, which we call B vertex, called secondary vertex. So secondary vertex should be well reconstructed, because they are coming from it is coming from the 2 muons coming from this secondary vertex, and you have a primary vertex there. And the momentum of these 2 muons should be aligned with this flight direction. So flight direction, when I say it's like primary to secondary vertex, if you draw a line, that should align to the momentum, resultant momentum of the 2 muons, and and that is one of the strong parameter actually to suppress the backgrounds from other decays, where the 2 muon resultant momentum may not be same as the vertex, the primary to secondary vertex directions. Not only that, even though there, as I said, this is experimental clean and theoretically also clean, but still you can see there is a huge amount of backgrounds that we have to deal with, and few of them is basically 2 semi-leptonic decays, where the 2 muons are coming from the 2 decays, or you can have one semi-leptonic and one hadronic B decay, or you can have even a BS decay to completely hadronic, like KK, and where 2 K1 by mistake, I take it as muons, or this one of the K1 gets mistaken, like misidentified, we call is as a muon, and you lose the neutrino here. So neutrino is lost, your detector doesn't catch it, and K1 is misidentified as muon, and then it gets BS to mu. Those are very important. And so you try to suppress them. As you go suppress them, in the end, you try to see actually how the B mass looks like. And you can see the beam, this is how the 2 muon invariant mass looks like. And there is a clear BS peak there. And however, the BS mass and the BD mass are very close to each other. Like this is 5.29, and this is about or 5.28, and this is about 5.365 there. So separating BS to B mu is very challenging for us, and one of the motivation to go for the detector upgrade, where the resolution, if you can shrink this resolution or make the resolution finer for the BS and the BD, maybe they will just separate that out naturally. And that's what we want to do that in the detector, and we'll see how it works in the upgrade. And that is the contribution from all these lower side the bumps, and coming where you lose one of these particles, or you lose one of, for example, one of the pions or neutrinos, and or maybe one of the particle gets misidentified, and then it just shifts to the left, the invariant mass. And the more that is one of the challenge where we have to look at to estimate properly when you are looking for the rare decays of a few events. And similar way, you have one of the, this is called kind of irreducible background. This is on the left side, they don't peak at around the signal region, but this is one of the background is very important, that kind of that peaks right underneath your on your signal peak. And those are like 2 hadron decays where the 2 pions or 2 kaons are they are kind of misidentified muons, and they will actually just peak. They will shift a little bit, but they will peak right underneath. But you can see on the Y scale, the amount is not it's not huge, but still reducing more and more is in a sense it's very important when your BD, the number of BD is not significant at this stage yet. And these 2 plots are basically, we have some final selection variable called BDT. Rather than applying cut on the BDT, we just separate the BDT with the lower region and higher region and fit the B mass in 2 different regions. And that's how it looks like. So,
Sanjay, I had a quick question.
Yeah.
Just go 2 slides back where you showed limits. Yeah. So on the right hand, these are all limits, right?
Yes.
The right hand side, when you start showing this error bar on this last red point, what does that mean?
You mean these points, right?
Yeah, this point.
These are experimental error bars.
That's not a limit. By that time, it's been seen.
This is the no BD.
Not this for B0. Yes, I beg your pardon.
This is the BD I'm talking about.
For
so
BD especially.
BS is just, it is already seen. The top.
BS is fine. Yes, BS of course.
It is the BD actually where we put the. But I think this is the just the upper limits, and I agree. What you are saying is basically what this error bar means. I do not think this error bar really shows. Maybe we can go.
If I may interrupt, Sanjay. Yes. I apologise for jumping in. No, that the paper you cite there, it does give a central value for the B0 because there is a hint of a peak. So it reports it, but it's not significant, and indeed, with more data, the significance has decreased. So in reality, there are only upper limits, but you will find a central value reported, I think, in that paper. That may be what's plotted there. I don't know.
Yeah. So this, Amol, this certainly this error bar will for BS probably true, but for BD it's not true because BD we put only the upper limit. We don't give the branch fraction.
Thanks.
Yeah. And you will see from this particular plot here, actually, And the BS from the CMS, I will show you the combined one. CMS, you can see about this is the experimental errors. And BD, there is just the upper limit. So we don't put the branching fraction. We don't have enough statistics to put the branching fractions. And also you can measure the decade effective lifetime for the BS. And recently people have started not only look for the branching fraction as well as look for the effective lifetime. And that's one of the results from the effective lifetime. You need a lot of statistics. So, whether it's a branching fraction or the lifetime, you can see the statistical errors are enormously high compared to the systematic error. And even though you get the data like 10 times more, the statistical error, keeping all the detector performance, everything same, the statistical error can go down 1/√10. And that is best we can do. So that's why the detector upgrade, making it is not only just going by statistics, also the performance of the detector is really makes very important actually. And one of the right side shows one of the diamond events, clean diamond events actually from the CMS. Also, this LHC, all the CMS Atlas and the LHC, we try to combine the given the importance of this particular decay mode, combine the events, and this is BS2 combined events for the 3 different experiments. There are contours 1 sigma, 2 sigma, 3 sigma contours, but the combined one also you can see there are like the standard model, and this is the experimental measurement, and they are kind of far away still, although it's not it's about 2 sigma away, but still it will be really interesting like to squeeze this experimental error, which is like huge experimental error. You have to squeeze them in order to see any significance there. And that I show actually just as experimental error, how much like even the combined result, experimental error is more than twice, almost 3 times the standard model right now. So, okay, the other things we do in the CMS and the B physics is look for some of the decays is like related to charmonium resonance, and this is very, very important in a sense. Some of these exotic hadronic states like a Z 4430 was discovered in fact in one of the B decays when people are looking for B going to psi prime K pi, and it showed up in the psi prime pi mass spectrum. And so quite often these charmonium states are looking for charmonium states. Different decay modes are very interesting, aiming towards searching for some hadronic exotic hadrons, as well as also looking for the standard model validity. And so where it says like a B0 going to you have jet psi, which is going to 2 muons and pi pi, and you have a k short which flies some distance, then going to 2 pions. And if you have a B going to just psi k short, psi prime k short, then you don't have to look at the 2 pions in the blue color here, and you see this nice clean peaks there for the BD, and this is going to BS going to jet psi prime k short, and this is basically BD going to B0 going or BD going to psi prime k short pi pi, and that's the branching fraction. The other ones was done recently was cross-section measurement for the BC B sub C 2s and 2s star plus. So these are the excited states of BC, and so it can decay to BC star, can decay to BC BC star plus 2s can decay to BC star plus, or BC plus 2s can go to BC plus, and where the BC can decay to J psi pi. So in the final state, you have basically nothing but and this decay happens to the 2 pion decay. So basically BC star plus 2s will decay to BC star plus 2 pi, and then BC star plus 2 pi will go to BC plus along with a photon, soft photon, and then BC plus will decay to GF psi pi plus. And because the photon is so soft, you will not be able to recognize it. So normally what you will see, all you have to look at actually BC pi pi, not BC pi pi gamma. So you look at the BC pi pi, and because of the unseen photon energy, you will see there are two peaks shifted, and one for the BC plus 2s, another is for BC star plus 2s. And that is what you see here. This is basically GF psi pi plus, which is basically BC plus, which is going to GF psi pi plus. And then you add with the 2 pions, and then you look at the BC 2s and BC star 2s. And this shift in the energy is basically because of the soft photon, which you missed out. And we are not looking at their masses, we are looking at the mass differences, because this by looking at the mass difference, some of the resolution effects cancels out, and that's a nice way to look at it. Also, CMS observed one of these particles called the cascade B stars, excited states of cascade B, and this is several of these resonance states have already been observed. One of these states basically looking at where cascade B is basically is a BS with another Q quark, which either is up quark or down quark, and so B is the heavier quark. So if you look at here, just the spin of QS means basically the combined lighter quark or combined spin, and this is the total spin of the whole states, and that's the angular momentum of a B with respect to the QS states. And the final state you can look up is basically the cascade B star is going to cascade B pi pi, and the cascade B decays to GF psi sigma or GF psi lambda k, and GF psi going to 2 muons, and the sigma going to lambda pi, lambda going to proton pi. So whole decay chain, and it is kind of shown here in the schematic way. And some of these dotted lines show because they have a kind of they decay, they fly some distance. However, the cascade B star, the expected flight length is very small. So that's why when cascade B star decaying to cascade B pi pi, we do not, the pi pi, we just kind of put them, we vortex them to the primary vortex, because they don't fly, cascade B star don't fly that far. And you can see here actually the cascade B candidates in the GF psi sigma and GF psi lambda cases, and this is the GF psi sigma, this is GF psi lambda k. There is another decay which is basically called the GF psi sigma naught k, and that is basically on the left side, where sigma naught, this is sigma naught is nothing but a lambda and photon, and if your photon is missing, then it will show up in the left side, and that's what it does. And then in the end, you just look at the mass difference of cascade B star with cascade B, and you can see there is a clear, nice, more than 5 sigma significance signal there, and the width was the measurement for the here was basically width measurement from the CMS. One of the recent papers that has been submitted to Nature Physics is a triple GF psi production in the PP collisions, and this is still not yet published. So this is this is not BD case, but this is very interesting in a sense, like more than one, when you have 2 proton collide, most often it's a single parton versus parton collide. But depending on the, as you go to higher and higher energy, there is a possibility of 2 partons or 3 partons, 2 partons or 3 partons, they can collide, giving rise to 3 charmonium states. This has been studied before in the other sectors, like in the heavier states, but GF psi, the charmonium state, it was never observed before. And you can see the cross section for this triple GF psi going from proton, and that's the cross section. And from this cross section, once you know the sigma, once you know the sigma PP going to triple GF psi, you should be able to extrapolate the information about the double pattern scattering and triple pattern scattering from this, and which I will show you in the next. And this is the naive way of showing so basically what this left side is basically proton-proton colliding to giving the triple J psi is here on this one. And this is the effective TPS. Effective TPS is kind of like a geometrical. So it's how much this proton-proton geometrical, they kind of the patterns they overlap, and that can be calculated. And these are the single pattern scattering. So you can have 3 pattern scattering related to the individual single pattern scattering, and that's the relation. And this M is basically is the integer that basically to take into account the double counting, whether you are looking at the 3 J psi or different particles. You can see now we have this is the 3 J diamond states, which is basically 3 J psi states, and you can see there are like more than about 5 to 6 events there in our data. And using this, you can calculate the cross section, and I showed you earlier, and that's the cross section about 272 femto1. And these 6 events, you can actually look at their 2 muon states. You can look at how far they are. Are they coming from the proton-proton collision, or they are coming from the non-proton, the J psi produced in some not coming from proton-proton collisions? So there is so P here is basically prompt decay, and this is non-prompt decays. So you just try to look at their flight length and how far they fly this the vortex of J2 muons from the primary vortex, and accordingly you separate them whether they are prompt or non-prompt events, and then the total DPS double pattern scattering cross section is related to all the single pattern scatterings in this relationship. And with that, you can calculate the effective DPS. Once you know the DPS, you can calculate the effective DPS. If you know the DPS, then you can calculate the effective DPS, and that's how it is calculated. And there are several other analysis experiments. They have performed the similar sigma effective DPS, and you can see the top one is basically coming from the CMS. Now most the recent one, and the other one is basically prompt open charm production cross sections, which some of the things we have never tried to explore in CMS for a long time, but this is the something that we looked at prompt one, and the open charm is basically the Mahajans with a single C quark with another quark. And what we are basically looking for this proton, the charm state coming directly from proton-proton decay, or maybe this is charm coming from the excited state of the D Mahajans. And these are some of these selection criteria we apply to make sure that we make sure they are not coming from the B decays. Also, not only that, they are the backgrounds are suppressed. And eventually, this what we measure is basically the function of PT and eta. You look at for the D, and you look at the cross section and compare with the different theoretical predictions or simulations. And you can see, for example, this shows as a function of PT for different experiments, CMS, Atlas, and there are some theoretical predictions. And this is as a function of eta also. You can see there as a comparison, you can see not a, for example, here, none of these is single theoretical predictions or the simulations, they match over the entire range. Maybe it is some cases matching in the lower side, but there is a mismatch on the upper side. And that gives a very good idea about because some of these things are theoretically very hard to calculate, because these open charms cross section, when you calculate, you get very close to the charm thresholds, and near the charm threshold, the theoretical predictions uncertainty gets very big. That's why some of these constraining some of these things from the experimental is very, very important. So I will talk about next 15 minutes on the detector upgrades. So one of these things you saw, actually, I talked about the BS to MIMU or BD to MIMU, is the problem is the BD and the BS, the mass, they are not properly separated out. And the question is basically, as you go to higher and higher luminosity or the more and more data, you may get more statistics, but but it is not essentially that still is making the resolution of these beam agents is very, very important. That needs the detector upgrades. And here it shows actually how the in the 3 octopan data in the CMS phase 2 upgrade. I will tell you what phase 2 upgrade is later, how these things can basically in the different eta regions. In the end cap, it is a little bit difficult, but in the rarer regions, and you can see in the they're kind of a little bit separated out, and we hope that it gets better for sure. And that is the one of the reasons why it has to be we need detector upgrades. Another thing I think you just saw in the morning, P5 prime, actually there was a huge discrepancy in the data on Monte Carlo, and that needed you need a lot of statistics, and not only statistics, you need to reduce this statistical as well as systematic uncertainty. And what you see here is with the current error bars, and the inner ones are statistical and the outer ones are the systematic one. In the each blue lines has a cross line there. But in the phase 2 data, we are just hoping that it will come down to the boxes here, and then that would really give good information about comparing with the theoretical predictions. And similarly for the JEP-Sci-Fi, I want to skip few slides because I have a lot of upgrade detector upgrade slides. One of these things also is Higgs going to in the Higgs coupling, and you can see like the Higgs coupling to C-quark or to EE, they are missing, and even mu, they have actually large statistical errors. And it is very important that we bring it down, and not only we have to reduce the background and increase the signals, and that needs the not only it needs more statistics, will not reduce the background, increase the signal. You need a better detector, and so these are some of the motivations why we need actually better detectors. Let's go to the CMS upgrade. What is the upgrade conditions? We are hoping that will go the instantaneous luminosity will go 5 to 7 times more than the designed luminosity, and the pile up the number of proton collisions every time the bonds crosses 25 nanosecond bonds crosses. That gets up to, as you see, like as the luminosity increases, the pile up got increased and increased. You saw earlier slide. And now when you have 200 such proton-proton collisions, it's extremely challenging to keep up with this data taking, as well as to all these tracks will overlap. And that is very important that your detector can separate the tracks. And that if you cannot do that, otherwise it will deteriorate. This condition will itself deteriorate the identification as well as reconstruction efficiency. And so we need a detector that maintain excellent performance for the in terms of efficiency, resolution, and background rejections for all the final state particles. And and so this again coming up with the same thing. And another thing is basically as you go to the higher and higher luminosity, you have like more than 150 collisions. So much particles come out, lot of radiations, and you can see this radiation levels. It's coming. This is the interaction point, and the red is basically higher the radiation doses. You can see this radiation doses gets more and more as you increase the intensity of the beam. And you have to have not only better detector, you need to have also electronics that can sustain that kind of a radiation doses for next 5 to 10 years at least. Yeah. So the CMS was planning to upgrade in 2025 because of that was our plan, the long shutdown. But due to COVID and many other reasons, it has been moved by 1 year. Not only that, the long shutdown period also was supposed to be 2.5 years. Now it is increased to 3 years. So that essentially pushes back our Run-4 data, taking from 2017 to 2029. So, but we'll be start taking Run-3 data. Will continue this year onwards till 2025. That will be the Run-3 data whole period, and that's that till the LS3, which so all this phase 2 will be basically happening in this LS3 time. So there was some detector upgrade already happened earlier. During shutdown, there was some small detector components are pushed in, but major detector components comes in, and there are some detectors which are completely new. And here this shows the phase 2 upgrade has a new detector, is completely new detector, is basically MIP and timing detector that is in between basically the tracking detector and calorimeter, and there is a GM detector, and some of them will be basically upgraded detector, and there are some basically just a replacement of the electronics. There will be some part of the detector upgraded, but mostly electronics upgrade, but there will be more detector upgrade on this side actually. So one of these things is when you have more, what are the upgrades? I'll just go very briefly one by one. So the level 1 trigger, when you have a huge number of luminosity and pileups, lot of proton-proton collision hitting in the every time bonds crosses, you have to absolutely make sure that your at the trigger threshold, your trigger works in the performance is really good. And so you have to have a sophisticated algorithm to choose to decide which events to keep, which events to remove, and that not only that, the bandwidth for this level 1 trigger will be increased from 100 kilohertz to about 7 times more. The latency right now about 4 microseconds. So there's a latency, this the time where the trigger has to decide whether he should keep that data interesting or not. And that goes from 4 microsecond to about 12.5 microsecond, about 3 times more. And that gives a lot of leverage for the experiments to pick up the interesting data actually. And that is just based on the many the detector upgrades. The tracking detector is one of the just outside the beam pipe, the tracking detectors, the pixel detector, and then you have silicon sensors or silicon tracking detector we call. So they are basically now the upgrade is going to happen to make sure. First thing is basically very important is you have to reduce the material budget. This is the current one, phase 1, and you can see the amount. So this is that radiation length 1.4 means basically tells you actually how much material is in front of that particle when it passes through. And with you can see this amount of material that will pass through the new detector is going to be significantly reduced. And that is in a sense very important if you have particle going through and the multiple scatterings. You don't want thick material in front of it so that it goes through and does multiple scattering and changes its direction. That's so for the tracking point of view and getting the vertex positions, it's very important that you reduce them. And so we'll have a 4 barrel and in the inner tracker and 6 in the outer, and that will vastly reduce the materials. And not only that, one of the very important things basically CMS is going to have now the tracking detector will be used in the L1 triggers where you look for the stops, the hits in the in the one of those layers, and look for the another hits just around this point. If you find the around this point, because of the large magnetic field, you can find some track hits actually in the around this point. If you find it, then you keep it. If you get that the second hit very far away, then you just keep you don't keep it. So that is the kind of algorithm you use it to keep some interesting events where the track hit goes to goes to more than track which is more than 2 GeV. And the detector performance, you can see here the PT, the error on the PT as well as the impact parameter resolution, you can see that significantly from the phase 1 to phase 2, it is significantly increases. Not only that, the occupancy also gets, you get very, the occupancy level is very small actually. The one is the timing detector, that is the new detector that will come just outside the silicon detector and inside the calorimeter. And this is really it's, good in a sense. It has a timing resolution of 30 to 40 picoseconds. So when you have like a 200 or 150 pileup events, where the RMS spread of this pileup is like 200 picosecond, so you just make sure that you. This is one way to you kind of split each of these pileup events into 40 picoseconds exposures, and that keeps you in the same pileup level as right now we are going through, like a 40 to 50. And that is very important. And not only that, it just gives you the 4D vortexing, because there is one more timing axis added to the not only XYZ, there will be timing parameter added to, depending on which time the particle go through the detectors. I will just skip some of these barrels, end cap barrels. That would be basically this is the timing. This is the same timing actually detector in the barrel and the barrel and end cap regions. They will be different detectors just depending on the exposure, because the barrel and end cap, they would have different radiation level. So the detector technology and the detector they are very different. And this. The other one is basically we go for the high granularity calorimeter in the end cap, and we have electromagnetic as well as hadronic sections, and we plan to have electromagnetic calorimeter. We will have a silicon technology and with these kind of observers, and that going about 28 layers, and the hadronic calorimeter in the end cap regions is going to have scintillators, either silicon or scintillators, and with steel observers that giving to about 10 interaction lengths. And that really, this is completely new, and they are in the hexagonal structure to make sure that it is the you maximize the geometrical area of the wafer, and this is how it looks like. Okay, I'll just go very quickly in 1-2 minutes. And the muon detector, we have, as I said, we have now the GEM detector has pushed in for this GE11, and but I think we have some of these new GEM detector coming up in the next phase 2 upgrade, as well as some of these detectors are some like RPC will be improved with the IRPC, which is multiple gap resistive chambers. But most of the improvements will be in the electronics and to deal with the level of exposure that we will be getting in the high luminosity LHC. So summary, CMS has produced more than 1100 papers so far, but still plenty of results is going to come out with Run-2 data. And we are gearing up for Run-3 data now, and the beam is on with higher energy. And so we are hoping that we'll start with the higher now center of mass energy with more than 13 TeV. There is a lot of challenge in the detector wise, a lot of challenge for the LHC conditions, but it will give us new physics to explore a lot of new physics in terms of physics outputs. And in next few years, it will be interesting and a lot of data coming. So let's wait and see what happens. Thank you.
Thank you very much. That was a great tour through current and future physics of CMS and this very ambitious upgrade. Are there any questions? Please raise your hand if you have one. While people are thinking, maybe I had a couple.
Sure.
One concerns the beta mu measurement, which you described very clearly, and the future prospects. So if we look at the current CMS measurement, I think that there is a systematic coming from the fragmentation fraction. Yes, that 0.2. So I'm wondering how this will be dealt with in future, because this is from the normalization, I think, to the beta J psi K channel.
Yeah.
So I'm wondering, as you'll increase your sample sizes much to a great degree in phase 2, how will this uncertainty be handled?
I don't think the phase 2 upgrade, this fragmentation uncertainty was dealt, but I think honestly, I don't know how to answer, because because it's you should be expecting the new results sometime soon from CMS now, and but how much it decreases, I think whether in the phase 2 upgrade it will significantly decrease, I'm not sure, I think. But I think probably as you get more and more statistics, then you know the curve as a function of PT and eta, there is a huge statistical error in terms of in the PT beams where we extract FS over FD, and those are very much, as you got more and more statistics, it gets better. We'll see. Yeah.
Okay, there's actually another question on BS to mu mu. It's been posted in the chat. I don't know if the person wants to actually just give it verbally, otherwise we can read it.
Yes, I can read it. Yeah. Hi, Professor Swain. Thank you for the nice talk. I have a question. I'll just read my chat. So I have a question on the approaches to B sub S mu plus mu minus by the CMS and the LHC B. So to pinpoint, I just want to know which does better in which aspect.
I think they are very comparable, competitive. I think I would not say which one is better. I think you can look at here. That tells the results. Here is CMS and LHCb, and the CMS is the green one and LHCb is the blue one, and they are not very different actually. They are very competitive, and the 1 sigma. You can just look at the 1 sigma level. The ellipse, and they are very competitive. Yeah. But it will be very interesting to see in the as you got the new data and with a better detector upgrade, that would be really interesting to see actually how the LHCb performs compared to CMS. Yeah, but right now I think they are very competitive. Yeah.
Thanks.
Maybe I can ask my second question. That again is about the upgraded detector, the phase 2 detector. This track trigger, which looks very exciting. So you explained clearly how it worked. So I'm wondering to what degree this will improve the B physics, because you have the possibility of triggering on decays which do not involve leptons. If I understand. How far has been investigated?
Yeah, but you can see here that the impact parameter, the improvement in the impact parameter is significant here, and that would really specifically when you are looking for the vortex separation, and that would really make a for the BDKs, it would make a really big impact actually. Even though it is a muon triggers, yes. Yeah.
Okay. Okay. Are there any other questions? Well, if not, let me thank you again. That was a very good pedagogical talk, and we learned a lot.